Hello, and welcome to the Chapter 2.1 online lecture on slope fields and autonomous equations. A slope field, or direction field, synonyms of a first-order differential equation, dy dx equals f of xy, is a graph using line segments of the slope at every point x comma y on the Cartesian plane given by the differential equation. So this differential equation is literally saying that the slope dy dx at any point x comma y is f of x comma y. Let's illustrate with the differential equation that we've already seen. So dy dx equals x over y. This is a differential equation that we saw, and we verified that it has a solution x squared minus y squared equals c for c an arbitrary constant. And at each point x comma y, it has a given slope. So for example, at 1, 2 at this point, then plugging into x over y, the slope is 1 over 2 or 1/2. So we draw a little line segment whose slope is 1/2. At 1, 1, it's 1 over 1. So that's a little line segment of slope 1, etc. And to satisfy this differential equation, well, we need that the slope at every point be that. So any solution must have slope x over y at each point, and thus lie tangent to each of these little line segments in the slope field. Let's verify that. We verified that this is a solution. So here's x squared minus y squared equals c for various c. And we can see that for each of these solutions, then the slope lies tangent to the slope field at every point. Obviously, the slope field, it only illustrates it for integer points, but every single point, including decimal ones, has a corresponding slope there, and the solution lies tangent to that slope. And this is a nice way of visualizing why a differential equation has multiple solutions, because depending upon your starting point, then what you need to do is follow the slope field from that starting point, and you get a solution. And you can start at any point, really, and you'll get another solution that lies tangent to the slope field. Let's modify this differential equation slightly, and maybe you can guess what the solution is. So dy dx equals negative x over y. Here's what the slope field looks like. So looking at this, what do you think the solutions are? What shape? If you guessed circle, that is correct. So along the circle, then it lies tangent to that slope field at every point, and a circle of any radius does, and that's our family of solutions. So as just illustrated, we can use the slope field of a differential equation to get a feel for what its family of solutions looks like, and the end behavior of those solutions. So for this slope field, beginning at, say, this point, we have to follow it. So it goes down and then back up, following the slope field, and we get a solution. And depending upon where we start, we can visualize the family of solutions from that slope field. Now, a first-order differential equation that can be expressed in the form dy dx equals f of y, i.e. the slope field is solely a function of y, x is irrelevant. This is called an autonomous differential equation. These are also called time-independent differential equations, because often that independent variable will be time. We want to modify the behavior of the system as a function of time. So if there is no time that goes into what the slope is, then it's time independent. The rate of change of the system only sees the current state of the system. That's what f of y would be. It's only a function of the current state of the system, not the time. And these occur everywhere in nature because there is no objective, what time is it in the universe? Things vary according to their current state. So here are examples of autonomous differential equations. dy dx is sine y. There's no x in that. Y times y minus 3, no x in that, no x in that either. If there's no x on the right-hand side in standard form, then it's autonomous, time independent. Now, slope fields of autonomous differential equations are easy to make, and that's because the slope is the same along all horizontal lines. A horizontal line is a line of time, and it's the same at any time. So for example, if we find that the slope here is 1, then it's also 1 there, it's 1 there, it's 1 there, it's 1 there, etc., because it's time independent. So let's sketch a slope field of this differential equation. So what we can do is plug in. So y prime of 0, for example, technically 0, 0, if we want to be precise, but it's time independent, so it doesn't care about the 0 that corresponds to x. It only cares about the y input. That would be 0 times 0 minus 3 is 0. Let me color code that. So that's a slope of 0 at 0, 0, and it must be the same no matter what time it is because it's time independent. Y prime of, say, -1. Again, we don't care about that x value really. You can plug it in, but when you plug it in, you don't plug it into anything. That would be -1 times -1 minus 3 is 4. So we have a steep upward slope there, and time independence is the same no matter what time it is, no matter what x is, etc. At y equals 1, it's 1 times 1 minus 3 is -2. So we have a downward slope there, and it doesn't care what time it is. Plug in a couple more points. Here it's also -2. Doesn't care about the time. And one more. At 3, we get 0. Slope of 0 there, doesn't care about time. We can continue. Imagine plugging in a number bigger than 3. We have something bigger than 3 times something bigger than 3 minus 3. That would still be positive. So we have a positive times a positive is positive. So up here we have a positive slope, and it's just always positive there. And same with if we plug in a number below 0, plug in a negative, we have a negative times a negative minus 3 is negative. Negative times negative is positive. So anywhere below 0, we have a positive slope. So that's a sketch of the slope field. Okay, now in black, let's sketch some solutions. Okay, so hypothetically, if we began, say, right here, we have a positive slope. So we are going up, and our solution looks like that. And moving to the left, here's a key thing. It's positive slope, yes, but it can never pass this line or sequence of slopes of slope 0. Because as we approach it, the slope is ever more becoming 0. So it will be smoothing out to slope 0. So it can't suddenly, go like that, because that would be a slope than 0 passing through where the slope is 0. So that's a contradiction. It just can't do that. So it has to be continuing like that, approaching. If we were to say begin here, then okay, to the right, negative slope, we're going down. And for the same reason, we can't ever cross that line, because as we approach it, our slope has to be approaching 0. So we have to be approaching slope 0 like that. We can't cross it because then we have a slope less than 0 through where it has to be slope 0. Can't happen. Okay, and to the left, negative slope still, and then we're approaching that line in the same way. And down here, if we were to begin, say, here, positive slope increasing, we can't pass that line for the same reason. So you can see that slope fields allow us to sketch what solutions to the differential equation look like. And critically, where the slope is 0, then that tells us what asymptotes there are, or potential asymptotes at least. And speaking of that, they critically tell us that these are called critical points. So a critical point, or equilibrium point, synonyms of an autonomous first-order differential equation, that's a 0 of f of y. A 0 of f of y is where f of y is equal to 0, so i.e. where the slope is 0. So in this case, 0 and 3, those y values where the slope is 0, those would be the two critical points. Critical points are important because they give equilibrium solutions, which are solutions of the form y equals c for c a constant. Why is this? Well, it's because if dy dx is 0 for all x, well, that means that y must be constant. only a horizontal line has slope 0 everywhere. So over here, if we imagine that we begin, say, here, we're at slope 0, just always at slope 0. So that's an equilibrium solution, because in practice, that would mean that if our system began there, then it just stays the same. It's an equilibrium, as we would say, is not changing like these other solutions. Likewise, if we began here, slope 0, so that system would be an equilibrium. Okay, so this is just a computer-generated graphic of the slope field for this, which is what we found manually. It is this slope field that we found over here. So we already found the critical points graphically. Let's find them now algebraically. So find the critical points. That means where is the slope 0? Well, that means we want dy dx, which is y times y minus 3, to be equal to 0. Remember that if a product of two things is equal to 0, then one of them has to be 0. That's typically the main point of factoring, really. So from this, that means that y is 0, or y minus 3 is 0. So y is equal to 0 or 3. These are the critical points. So that means that the equilibrium solutions are y equals 0 and y equals 3. Those are the two steady state or equilibrium solutions that we found graphically earlier. So as you can infer, the point of this section is being able to understand graphically and at a point intuitively what the behavior of differential equations looks like, even if we can't actually solve those equations. Not only in terms of these equilibrium solutions, but also in terms of what other solutions look like. So as we found, the other solutions must look something like that. Now, slope fields are great, but for autonomous differential equations, they're kind of superfluous in the sense that it doesn't care what time it is. So the slope is the same along all horizontal lines. So we may as well just take a single cross-section of it, like this. And in that cross-section, we can see that it has positive slope there, it has negative slope there, and it has positive slope there. And these are the two equilibrium points. And this picture, that's fundamentally all that a phase portrait is. So make a phase portrait of this. Well, this is the phase portrait of it, actually, inferred from the slope field, but we're also interested in being able to make these algebraically without having to plug in points and make the slope field. And to do this, it's actually the equivalent or analog of sign testing from pre-calculus. So let's make a phase portrait of this algebraically now. We should get the same thing. In making a phase portrait, step 1 is to find the critical points. And we already found on the previous slide that they are y are 0 and 3. Step 2, we sign test between the critical points. So we begin making our slope field algebraically like this. We have found the critical points, we'll denote those. And by sign testing between the critical points, we mean the following. When y is less than 0, we'll plug in a point less than 0. So we'll choose, say, -1, y prime of -1, that's -1 times -1 minus 3 is 4, is positive. So that means that down here is increasing. And by the way, why must it always be increasing there? Well, the only way that the slope can transition from increasing to decreasing, hypothetically, is for it to pass through a place where the slope is 0. We can't go from a decreasing slope here to an increasing slope there without passing through a critical point. Since the slope must vary continuously, and we can't ever pass through negative to positive slope without passing through where the slope is 0, but that's a critical point, and we have already found all critical points, so it can't possibly transition from upward facing to downward facing down here. That is why we can determine the slope down here by just plugging in any point in that domain. We could plug in -1, we could plug in -5, we could plug in -10. No matter what we do, we'll get a positive slope because it can't be anything else. Okay, and now we test this other region. By the way, that's why it's called sign testing. The sign testing is testing if it's positive or negative, that kind of sign. Okay, so when y is between 0 and 3, that's our next domain. We plug in any point in that interval. We can choose any point there. Let's choose, say, 1. We have 1 times 1 minus 3 is negative. So we have a negative slope there. And when y is greater than 3, we can plug in at any point there. We'll choose, say, 4, plug in 4, and we have 4 times 4 minus 3 is positive. So we have a positive slope there. So we know that solutions up here must be increasing, solutions in here must be decreasing, and solutions over here must be increasing. And that is the process of creating a phase portrait algebraically. Yes, so phase portraits are an efficient way of deciphering the behavior of solution curves. So for example, depicted is the phase portrait of dy dx equals p times a minus bp. And by depicted, I specifically mean this part over here. That's the phase portrait. We could find this ourselves by finding the critical points. The critical points of that's where dy dx equals 0. That means that p times a minus bp equals 0. One of those has to be 0, or the product to be 0. So p is 0, or a minus bp is 0. So solving those, p is 0, or b over a. From this one, we move the a to the other side, divide by b, we get b over a. And then we could plug in points. That's in the sign testing part. When y is less than 0, we'll have, say, -1 times a minus b times -1. Remember, our choice there is arbitrary. We could choose -2 if we wanted to, just any number that's less than 0 would work. Okay, but that's -1 times a plus b. And the problem here, the phrasing should have specified that a and b are positive. So a plus b is also positive. So this is a negative. So we would know that down here it's negative. And we could continue, etc. And we would find the depicted phase diagram. And from that phase diagram, we could then sketch solutions. So it's negative there, so it's decreasing, and it always has to be approaching the equilibrium solution given by the critical point in at least one of the directions. Over here, it's increasing because phase diagram there points up and approaching where the slope is 0 and approaching where the slope is 0 in that direction. And up here, it's decreasing, approaching the equilibrium solution. And in this direction, it has to be increasing to the left, which is decreasing to the right. The decreasing to the right is that downward slope. So it's in this way that the phase portrait expediently gives the gist of what solutions look like. Now, the critical points, which are the equilibrium solutions, there are a few different kinds. There are attractors, repellers, and semi-stable. We'll talk about each of those first. Attractors. An attractor is a critical point where the slope above it is down and the slope below it is up. That's called an attractor because if that's the case, then as depicted here, the solution curves either above or below must be approaching it, and thus it's in a sense attracting states from both directions. On the other hand, critical points where above it has a positive slope, and below it has a negative slope, those are called repellers. For an analogous reason, above it, slope is positive, so it's kind of repelling away, and also it's repelling away below it because the slope is negative there. And lastly, there are semi-stable ones. Semi-stable ones are ones where it's mixed. So they're ones where it attracts from one direction, and from the other direction, it repels. So we could make a phase portrait for this in the same way that we've already done. It has critical points 0 and 3. There's our 0, there's our 3. And plugging in between them and above and below, when we're less than 0, it's negative. When we are between 0 and 3, it's also negative. Just plug in, say, a point 1. And when we're bigger than 3, say plug in 4, then it is positive. So it's semi-stable if the arrows in its phase portrait on both sides point in the same direction, because that pointing in the same direction corresponds to that we're moving toward it above it, if it's like this, and moving away from it below it. So y equals 0 would be called a semi-stable critical point. So in summary, here's a picture of attractors, repellers, and semi-stable points. An attractor C looks like this, where the arrows in the phase portrait are pointing toward it on both ends. It's a repeller if the arrows in the phase portrait are pointing away from it on both ends, repelling on both ends. And it's called semi-stable if it's one of these two cases, where it's either facing up on both sides or down on both sides. In either case, it attracts from one direction and repels from the other. Let's do a practice problem. I encourage you to try your hand at this. Pause the video where you want to find the phase portrait of this differential equation. Okay, so we have dy dx is y squared minus 4y. For the critical points, we want that the slope y squared minus 4y be 0. Factoring is always good because that allows us to solve. We get that y is 0 or 4. And now we sign test. When y is less than 0, say y is minus 1, we have that, well, negative 1 times negative 1 minus 4 is positive. Okay, so we have these two critical points. That already eliminates solutions, possible solutions A and D. Those have the wrong critical points. And we're left with just B and C so far, just from those two critical points. And from the sign testing, we know that when y is less than 0, then this slope here, plugging in minus 1, is positive. So it has to be like that, which eliminates this possible solution. So we actually don't need to go further. We could sign test the other regions, but we've already eliminated that one, and that one. And this one B must be our solution. And the next part of the problem is to sketch typical solution curves. So take a moment, pause the video, and identify which of these has the typical solution curves to this differential equation given the phase portrait that we found. Okay, so we know that it has those two critical points, 0 and 4. So we can actually already eliminate two of them. Those have the wrong critical points. Remember, the critical points correspond to equilibrium solutions, which correspond to asymptotes. Okay, and from our phase portrait, we know that the slope is, say, positive there. And for this one, what's the slope when we're less than 0? Well, this one has a negative slope, so it can't be that one. This one has a positive slope there, so that's our only remaining choice. That has to be what the typical solutions look like. And again, we could continue, it's decreasing there, and that's decreasing, etc. And lastly, a Slope field where a differential equation is shown. Which of the following is a sketch of the solution to the differential equation satisfying y of -2 is 1? So this is just a question on pure slope fields. Take a moment and see if you can identify which one. Pause the video. Okay, so this is an x value, and this is the corresponding y value. And what this means is that the point -2, 1 lies on the curve. Let's find those points on each one. And it really is that simple. There's only one curve here that contains the point -2, 1, and it's that one. If there were two possibilities that contained that point, we would need to look at which of those solutions were such that the slope of the curve at all points followed the slope field. So that has to be the answer. All right, and that does conclude section 2.1. Have a great one.